Some of the interactions we've discussed so far belong to a class we call contact interactions. The term contact here means the agent in the surroundings must typically be in physical contact with the object in order to exert a force on the object, in order to have an interaction. One example of this we've already discussed is the spring force. The spring must be in contact with the system to exert a force. No physical contact, no interaction. Now, not all interactions require contact. Newton's universal law of gravitation and Coulomb's law for electric forces are two examples where we can have interactions at a distance without physical contact between the system and the surroundings. In the next couple of lectures, we're going to discuss how to model some additional contact interactions that may arise between solids. Let's discuss first the case where we have a wire tied to our system. What we say here will apply, for the most part, also to strings or to ropes or to something similar attached to our system. If the wire is pulled taut, then the wire can exert a contact force we call tension on our system, which we'll label with the symbol F sub t. First, let's discuss the direction of the tension force. Simply stated, the direction is along the wire, away from our system. In our discussions, this is the only direction that a wire can exert a force. You can't push a wire, wires can't exert compression forces, and you can't exert a sideways shear force with a wire. Now, sometimes real wires can exert compression or shear forces. However, we're considering only the simplest cases involving wires here, so the tension force along the wire, away from the object, is the only wire force we'll consider. Now let's discuss the magnitude of the tension force. This is a subtle issue where there is no single answer because the tension force can vary, can adjust to fit the circumstances of the particular situation we're examining. To understand how this happens, let's start with a mental picture of the wire at a microscopic, at an atomic level. At this level, the wire is held together by bonds, chemical bonds between atoms. Typically, the nature of the bonds are such that the atoms in the wire are at a just right distance, not too close and not too far from neighboring atoms. This distance is called the equilibrium distance. Now, if the wire is pulled on, then as the atoms separate in the wire, there arise forces that try to restore the separation between the atoms back to the equilibrium distance. This is very much like the way the spring force we discussed earlier works, always acting to restore the spring to its natural relaxed length. So picturing the chemical bond as a spring acting between two atoms in what's known as the ball and spring model, where the atoms are the balls, is a common way to think about solids at the atomic scale. Now fundamentally, these chemical bonds aren't really microscopic springs. The bonds arise fundamentally from electric forces. This picture of the bonds as springs is a model which we're using just as a helpful way to think about certain aspects of the way solids behave. So let's use that picture for now as a way to think about tension as a kind of spring-like stretching of the bonds. So let's imagine we have a single wire, one atom thick for simplicity. When the wire is not attached to anything, the atoms in the wire are in their equilibrium positions. The bonds behave just like relaxed springs. However, if we tie the wire to some object, like this big ball shown here, and we pull on the wire, then there's a tension in the wire that we can think about as arising from the stretched bonds behaving like springs. We can now see how the magnitude of the tension force can vary depending upon the particular situation we're studying. Here, for this example, where we are pulling on the wire, then the tension force magnitude will depend upon the magnitude of our pull. The greater the pull, the more the spring-like bonds will stretch, and therefore the larger the magnitude of the tension force. This picture also illustrates another thing about the magnitude of the tension force. As long as the mass of the wire is negligible, say, compared to the mass of our system, then we would typically have the same amount of stretch everywhere in the wire, which would mean the magnitude of the tension force is the same everywhere along the wire. One final note here. Wires aren't typically one atom thick. A real wire would consist of many parallel chains of atoms, something like this. Nevertheless, what we just said about the connection between the stretch of the spring-like bonds and the tension in the wire that was one atom thick carries over unchanged to this case as well. So, in summary, in the model we'll use for the tension force exerted by wires and, as well, strings, ropes, and the like, the direction of the tension force is along the wire away from the system, and the magnitude of the tension force will depend on the particulars of the case we're studying. To practice this, we'll study some examples involving tension forces. We'll save that for a future lecture, which will be coming up soon.